Okay guys, so we talk about the periodic motion. We learned what oscillation means, we learned what restoring force means. We also looked at equilibrium position. So now let's look at this graph here. So we have something here. I'm gonna make this graph here. Let's go. What do you think, how do we model this function mathematically? So we have a graph, it goes like this. And then we have a time in second on this axis, and then we have a x in meter, right? That in that axis, and then it kind of starts. So I'm gonna make that, try to make that scale here. So maybe 1, 2, 3, 4, 5, and I'm not gonna do exactly. Okay, so do some of this, and then on the up side here, up is like 1, 2, still up to like 3. So it starts somewhere from here, right? And then it goes here. Oh, there is also down. 1, 2, 3. Okay. And then it starts from here. It goes here, and then it goes all the way up to here, up to here, and then it goes back again. So let's look at this. So it starts here. Up, goes back, comes down, goes up, comes down, and then goes up like that. Okay, so you could make more, but I don't want to spend time doing it. It's the same thing, right? We have enough information here. So how do you think we can model this function mathematically? So we have a function here, right? So this is a function of x, t. X is a function of time. How can you model this mathematically? Have you seen anywhere before, maybe in the math you have learned or anything? One thing we know is it's repeating with time, right? Alright, so it turns out that this is nothing but this function. We can model it as xt equal to a cos 2 pi f times t. Okay, so this is really a cosine function here that repeats, okay, here that repeats with the function of time. Okay, so this position here, xt, x as a function of, time, equal to a cos 2 pi ft. Okay, so this is what this position, right, position versus time graph look like, or we can model this graph mathematically using this function here. We call this type of motion as a simple harmonic motion. Again, the motion that repeats itself, over time. Okay, so simple harmonic motion. Simple harmonic motion. You will also see probably in your textbook or elsewhere, it is usually abbreviated as SHN. Okay? I want to explain you guys some of the things there. So this quantity A, this is cos some angle theta, like that, right? It's like, some A cos theta, right? Like that kind of thing, right? Some x equal to, x equal to A cos theta, something like that, but we have this, function of time. So now see this guy, so this is like theta here, argument here, right? This A is nothing. What do you think is this A? So this A has to do with the maximum position. Remember earlier I talked about amplitude. So this A is just the amplitude of a motion here. Okay, so this A actually corresponds to this here, guys. Either this, you could say, you know, it's supposed to come to close to the 2. Okay, so I was trying to make it all the way up. So this distance here, this highest distance, this one, or you could also look at it on the top, on this side. That's down or up. Okay, so but then make sure you take the positive value because amplitude is a length and it's positive. Okay, so this is a amplitude here we have here, or this one here is amplitude, the maximum displacement of the object. Okay, now and then T, you know, time. F is a frequency, so we are going to look at that in a few minutes. Alright, so this amplitude is important to note. Amplitude means the maximum displacement from equilibrium position. So look at our equilibrium position is, in this graph it corresponds to this line here when, you know, position is 0. Let's write 0 here. At this point, 0 here, okay? When time is 0 here, our position is also 0, right? So this line corresponds to the equilibrium position. And then so now let us look at, I want to illustrate this again about frequency here. So we had this, guys, over here, this is corresponding to this here, okay? Once it's in motion, it goes down, gets maximum, that value is our A, okay? And it comes back and it goes back again to the maximum, you know, compression, okay? So both of those values are A. One is in negative side and one is in positive side. So if you take this as an origin and if you down as a negative, then up as a positive, okay? Now this is happening not just one time, look at this. So look at this. So see, it is repeating over time. So when it does this, goes down, comes back to the, you know, equilibrium position and goes up again, compresses and gets to maximum A, and comes back to this equilibrium position. This is one cycle, okay? So that duration, the time it takes for this oscillation to, you know, complete one cycle is called period, okay? And it is represented by T. So period T, time to complete one full cycle. Alright, now this time, there is also, we also mentioned earlier about frequency. These two things are related actually. Frequency means number of those completed cycle in 1 second, basically, okay, or per second, per unit time. You may have heard that word, okay? So it means really, frequency, it is not the time, but it's the number of number of those completed cycle in 1 second, okay? So F is 1 by T, okay? So 1 divided by time is a frequency, so they are inversely proportional. So let's look at here. How do you think we can find here frequency? So our complete cycle, if you want to look at it, we can, you can start from here, right? Go from here and then make it like go up all the way up and then come back here. That's one cycle. Or really, you don't have to really do this part. You could also just do it from here. If you start from here, then what happens? You go down, and then go down, and then all the way come back here. Then that is also one cycle, okay? But it is often easier to kind of just look at, just complete full cycle, right? You start from here, from horizontal axis, you start here, goes, and then come back here, okay? One cycle here, okay? So the frequency is just the repeated, so the number of complete cycle, full cycle per unit time. So how many cycles do you think we have here? We have many here, but let's do an example, or let's try it, practice this. Okay, I'm gonna give you guys equations. So I'm gonna erase it. Please make sure you copy this. You will need this information. Okay, so a few things here, right? So I'm gonna write down this equation that will be helpful for you guys again. Okay, so guys, so put a scale. So we are given a graph here. Okay, so same thing here, just as this. So now put a scale on the position versus time graph for an oscillating mass spring system when amplitude is 0.2 meter, frequency is 2 Hz. So your job is here to put this scale. Where do you think is the amplitude? Find out that amplitude first and then put a scale here, like maybe on x-axis or y-axis. How would you mark a scale on the x-axis as well as y-axis? So please take some time, another 2 minutes or so, and then work on that, okay? Okay, so were you able to find the answer? Or were you able to put a scale here? Alright, so the result turns out to be this. So the amplitude is 0.2 meter, right? So we said amplitude means what? The maximum possible change in length, right? So the maximum displacement from the equilibrium position, in other words, okay? So this is the related to equilibrium position, maximum stress, or maximum distance from equilibrium position. We know our position, we have the position in the y-axis, so the maximum distance is length of this or length of that, okay? So you see here we have 0.2, so that's the amplitude. So we could put 0.2 here on the on this axis, okay, vertical axis here, on the position axis, okay? And then if this is a 0.2 on the negative side, we're going to have the minus 0.2 here. So we are done with putting amplitude scale for amplitude on the vertical axis. Now the frequency is what? So F is what? 1 over T. I already mentioned that. We are given the frequency 2 Hertz. So you see, if we are to do math here, then frequency is going to be what? We are given a 2 Hertz, right? So what we could do here is we could just write T equal to 1 over F, and then 1 over 2 Hertz is what? Half. So the period is half here, okay? Which means it is going to complete 1 cycle in this half a second, okay? So 1 cycle, it starts from here, it goes down, goes here, it goes here, and by the time it comes back, wherever it started, and it comes back to the same point, that time is the period here, right? So when we do that, and then if we take this point here, and then if we put a dot line here, go down here, then that is the half a second. So this is a period here. Period is half a second for this graph. Okay, so I hope that makes sense to you guys. Let us do a little more. Let's look at more things. Okay. Alright, so here is another practice question. So alright, so now here is the opposite of what we were doing earlier, and little bit extra. Okay, so we are given the position versus time graph here. We are also given a scale, and we are also given a scale on vertical axis as well as horizontal axis. Time is in second, position is in centimeter. Please note this down. Okay, earlier we had it in meter. Okay, so centimeter. You wanna determine the period. So here T equal to what? Period. Determine frequency F equal to what, and then amplitude A equal to what, based on this information, guys. So please try, give yourself a couple of minutes to work on this. So can you see this scale here? So on the time axis it starts at 0 here, and the first point that's touching this is 1. The second point here, second is 2, and then 3 and 4. So there is a 1 second division here, okay, on x-axis. On vertical axis we have it starts at 0. It goes by the first one here, this one is 0.01 centimeter. The second one is 0.02 centimeter. So the division, the division scale here is 0.01, okay, on the vertical axis. So even if you are not able to see it, you should be able to draw it on your notebook and then work on this. So please take a couple of minutes to work on that. Alright, so are you able to come up with any answer for this one? If not, that's also okay, so let's do it here, okay? So first and foremost thing, let's look at the amplitude, right? A is what? Maximum distance from the equilibrium position. This is the equilibrium position here. Maximum distance is this. are this here, and if we look at it, it starts from 0. The tip of this curve here is 0.05, so amplitude A is that, you know, the length, right? So 0.05 centimeter. How about the time? Again, we said time is the total time to complete one cycle. So if we start here, it goes down, comes back. By the time it comes back here, right? So it's like this. You start here, this point is important. We have to come back to the same, you know, height again, okay? So you start here, goes down, and then comes up, and then it gets here. So it is here, it corresponds to 4 seconds here, okay? So time is 4 seconds. Since now we know the time, we can find a frequency, because frequency is the inverse of time, 1 by t, okay? Inverse of time. So 1 by t is what? 1 by 4 hertz, okay? So that is the frequency here. Alright guys, so I hope now you are, you know, you can work on, you know, I think now you can find the time, frequency and amplitude if you are given the graph and the scale, okay? In the next video, we are going to, you know, further advance our knowledge in the, you know, position versus time graph, and also look at velocity versus time graph and so on.